Arrow Lake's Intel graphics has a lot of undervolting potential, but can we also use that potential to improve Llama 2 power efficiency? In SkatterBencher number 86, I illustrated how a 20% undervolt of the Intel graphics integrated in the Core Ultra 9 285K reduced the reported graphics core power by 40% in the OCCT 3D standard stress test. Today I want to have a closer look at using that undervolt margin to improve the power efficiency of AI workloads. And for that I'll use MLPerf Client, a relatively new benchmark that I've been playing with. MLPerf Client is a benchmark developed by MLCommons to evaluate the machine learning performance of consumer-grade systems such as laptops, desktops, and workstations. It focuses specifically on large language model performance. The first version, v0.5, was made available on December 11, 2024, with initial support for Intel integrated graphics. Just last month, MLCommons released an update to the benchmark, dubbed v0.6, with support for the Intel NPU, something Intel obviously liked very much. The benchmark workload is based on Meta's Llama 2 7B LLM. It's optimized for reduced memory and computational requirements via 4-bit integer quantization. I like MLPerf Client a lot because it's a great addition to the AI benchmark I've been using in all of my SkatterBencher guides recently. Whereas AI benchmark primarily tests perceptive AI performance, MLPerf Client adds to that with its generative AI performance tests. When evaluating the energy efficiency of AI systems, two metrics often come up: performance per watt and joules per token. Performance per watt will tell us how much computational work a chip can deliver for each watt of power it consumes. That makes it a preferred metric for comparing the efficiency of hardware itself, regardless of the model being run. On the other hand, joules per token measures how much total energy is required to process a single token, incorporating not just the chip's performance, but also how the model, memory access patterns, and system overhead affect energy consumption. While it's useful for understanding the cost of running AI models in production, it's less ideal for isolating hardware performance since it's influenced by model-specific factors. Furthermore, there's different ways to measure the power consumption. We have the option between three metrics: the graphics core power, the CPU package power, and the total system power. The first two metrics we can measure using hardware info as their values calculated and reported by the Arrow Lake CPU power control unit. The third metric we can measure using the BenchLab, an ATX-sized PCB that sits between the motherboard and the power supply. Note that the total system power doesn't account for the power supply efficiency, but rather the power draw of the system components from the power supply. With the Core Ultra 9 285K at default settings, the Intel graphics generates 14.49 tokens per second while using 68.93 watts on average for a benchmark duration of about 15 minutes. That translates into 0.210 tokens per joule, or 4.76 joule per token. Now we can have a look at the impact of overclocking and undervolting on AI workload power efficiency. I ran two configurations, one overclocked at 2800 MHz and another one undervolt by about 20% at the default frequency of 2 GHz. Note that the overclocked configuration also has slightly increased voltage according to the standard voltage frequency curve. For more information on how to overclock and undervolt the Intel graphics on Arrow Lake, I gladly refer you to SkatterBencher number 86. After undervolting the Intel graphics, we obviously generate the same 14.49 tokens per second. However, the graphics core's power is now 5.76 watt instead of 9.85 watt, which is a reduction of 41.5%. On a system level, the power consumption reduction is not as much, as it's only reduced by 2.6 watt to 66.33 watts, a 3.8% reduction. That translates into 0.218 tokens per joule or 4.58 joule per token. After overclocking the Intel graphics by 40% to 2800 MHz, it generates 16.62 tokens per second. That's a 14.7% performance improvement. While it doesn't sound that amazing, bear in mind that the operating voltage only increased by 4.8% from 0.978 volts to 1.025 volts. The system power consumption increased to 74.98 watts, an increase of 8.8%. That translates into 0.222 tokens per joule or 4.51 joule per token, an efficiency improvement over default by 5.45%. This result might be a surprise to some of you because usually overclocking doesn't improve power efficiency. However, as I highlighted in SkatterBencher number 86, the standard voltage frequency curve is far from the most efficient as it uses more voltage than necessary. At 2800 MHz, the curve is much more optimized, resulting in a better performance per watt. Next, I also have a look at the impact of enabling Intel 200S Boost and tuning the memory timings. As I illustrated in SkatterBencher number 86, tuning the memory subsystem actually has quite a big impact on the integrated graphics performance. We see the same with MLPerf Client. Enabling 200S Boost increases the performance at default graphics frequency by 10.4% to 16 tokens per second. Tuning the memory timings further increases the performance to 16.51 tokens per second. In terms of efficiency, however, the increased system agent and system memory voltage to 1.2 volt and 1.4 volt does more harm than good. Enabling 200S Boost decreases the efficiency by 14.39% from 4.76 joule per token to 5.56 joule per token. Tuning the memory timings improves it slightly to 5.48 joule per token. That makes sense because we're effectively optimizing the memory performance without increasing the operating voltage. This is a typical trade-off where we sacrifice some power efficiency in exchange for higher performance. Of course, we could try to lower the system agent and system memory voltage and claw back some of that power efficiency. But that's for another video or another YouTuber to try. One thing we can have a look at is increasing the graphics frequency to 2800 MHz because as we've seen in the previous segments, that actually helps power efficiency. With overclocked Intel graphics, 200S Boost enabled and tuned memory timings, the performance improves by 37.8% to 19.97 tokens per second. The total system power is 97.1 watts, an increase of 40.9% over default, which yields 4.862 joules per token. That's about 2% less efficient than stock, but of course gives us higher overall performance. In my SkatterBencher guide, I already highlighted that the standard voltage frequency curve of the Intel graphics for Arrow Lake CPUs is far from ideal. There's a lot of undervolting margin, and we can use that undervolt margin to improve power efficiency in a variety of workloads. For example, in this video, I illustrated that we can improve the generative AI performance in Llama 2 LLMs by about 40% by overclocking the graphics cores and the memory subsystem. Or we can undervolt at the standard frequency and improve power efficiency by about 4%. Overclocking the memory subsystem, the NGU and the system memory itself, will increase the power consumption and therefore have an impact on the power efficiency. But it also results in a lot higher performance. So that might be a trade-off you're willing to make. Anyway, that's it for this checkpoint. Leave a comment in the comment section below if you have any questions or suggestions. I want to thank the Patreon members and the YouTube members for their continued support, and I want to thank you for watching. See you next time.